Hey guys, this is Mr. Lewitt. I'm gonna prepare another little video tutorial for you guys. This morning I emailed two files to you, cartesianproducts.rkt and cartesianproducts.nb. So one of them shows you how to define functions to find Cartesian products in Racket, and the other one shows you how to find how to define functions in Mathematica to find Cartesian products. So let's look at a few of these problems. Now, remember, guys, um, I can't do a video like for every single homework problem that you have. You're going to have to do a lot of this on your own, but I'll try to help you out as much as I can and kind of point you in the right direction. And certainly my videos will have a pretty strong programming emphasis. How do you use Python or Mathematica or Racket to help, solve these problems? But, don't depend on me to solve every single homework problem that you have. All right, that's not how this course is set up. And actually, there are quite a few asynchronous online teachers at Oakton and other schools who don't even make excuse me, they don't even make videos for their students necessarily. This is something that I'm doing because I think discrete math is fun. I think it's interesting. I think Python is fun and interesting. I like Mathematica. I like Rackets. And I want to try to help you guys out. But, I can't do a video that's gonna, I can't do every single homework problem for you, okay? Because that's just not realistic. That's not a realistic expectation. Okay, so let's just focus on Python for right now. So we're gonna open up Python. I'm looking at problem number 30. I'm looking at problem number 30 in your homework. This is chapter 2. This is chapter 2, and I'm looking at problem number 30, and this has to do with the Cartesian products of sets. So let's see if we can kind of figure this out, okay? I know a lot of you guys love Python, so this should be kind of easy. All right, so how are we going to do this? Let's see, hold on a second. Okay, let's go to... Oh, wait a minute now. Documents, discrete math. And let's go into, how about, I'm going to go into this directory. Oopsie. Racket. Okay. Oops, no, that's not what I want. Jupyter Notebook. Okay. Okay. So let's see. How should we get started? So let me look at the problem. We have three sets. We have uppercase A is equal to ABC. Uppercase B is equal to X and Y. We have uppercase C. Set C is equal to 0, 1. Match the Cartesian products on the left column to their corresponding member sets on the right column. You know what? This picture is really in the way. Oh, come on. Why? Hold on a second. Why can't I move that? Okay, I can't. My picture's kind of stuck here. The picture in the lower right, that's really not good. Okay. Well, okay. Maybe. There we go. We can kind of, for God's sakes. Okay, well, we'll worry about it later. Yeah, my little picture here is kind of getting in the way. I should have just canceled that, but that's okay. All right, so let's break this down. So if you have a list, like 1, 2, 3, right? We have a list here, right? So I could call it, X. Okay, Shift Enter, and so this is X. So X has a head. X has a head, which is X0, right? And then the rest of the list is represented that way. Now that's really important, and it's the same thing, by the way, in math. Well, in Mathematica it's slightly different, because in Mathematica the initial index is going to be 1. In Racket the initial index is 0, but in Racket it's going to be, the syntax is a little bit different, but it's the same kind of idea. All right. So the thing is, let's start building a function that's just going to take an element and combine it with every element here in my list. All right. So what should I call it? First of all, I'm going to, we can get rid of that, and we can get rid of that. I'm double D, just pressing D twice. And this one, let's see, we can do delete cells. There we go. Okay. So define, what should I call it? Cartesian helper, element wise. This is just going to be a list. This is just a list, okay? And let's see. If not Boolean wise, return wise else. Now, if you're wondering, what is this? Okay, so, okay. If I have an empty list and I change it into a Boolean value, what do you think it is? It's going to be false. So false, when you take an empty collection, it could be an empty dictionary. It could be an empty dictionary. It could be an empty list. Okay, if you have an empty collection in Python, you change it into a Boolean value, it's going to be false. This is not the case in Racket. With Racket, it's a little bit different. But in Python, if you have an empty collection and change it into a Boolean value, it's going to be false. So what if I want it to be true? Well, just not. What's not false? Not false is true, right? And then you have not. Okay. Very simple, not a big deal. So let me just erase these because I don't think you need that anymore. So else, so what are we going to do? Okay, well, we're going to have to traverse the list. So what I could actually do, you know what I'm going to do? This is, I'm thinking, I'm using a more functional programming style here, and Python is not 100% functional. So I'm going to call that, what should I call it? Oh, I don't know. Result, oops, sorry. Result empty list. Return results. Else, okay. For y in y's, okay, result append element y. Now there is another way to do this with recursion that personally I like a little better, but I mean, you can do it this way too. Although, hold on one second. Yeah, we're good. And although actually, hold on one second. You know what? I'm going to get rid of this else because I don't think we really need it. In Racket, we would need it. Hold on 1 second. So if y's is empty, just return result. For y and y's, result dot append element y. I think we're good. Okay, I think we're good. So, okay. So, Cartesian helper, oh, I don't know, 1, 2, 3, 4, 5. So we have 1, 2, 1, 3, 1, 4, 1, 5. Perfect. That's exactly what I want. So we have 1, 2, 1, 3, we have 1, 4, and we have 1, 5. And that's looking really, really good. That's looking really, really good. Oh, and you know what? I think, okay, we are going to need this eventually from func_tools import reduce. And that's actually really important because we're going to need this. We're going to need this eventually. Not right away, but we're going to need this eventually. Okay, so Cartesian helper is looking good. Cartesian helper. Perfect. That's exactly what I want. That's the behavior that I'm looking for. Okay, so the next step is, instead of this argument just being like a single value, what if it's actually a list? What if it's actually a list? Okay, so let me think for a moment. Okay, so we're going to have define Cartesian x's, y's. Okay. If not bool x's or not bool y's, I'll do the same thing as before. Result is equal to the empty list. Okay. So if x's is empty or y's is empty, we're just going to return the result the way it is. I don't think in this case you need an else. Now Python's kind of weird this way. With Python, you can just have an if by itself. You don't need if and else. You can have an if by itself. In Racket, that is not going to work, okay? In Racket, if you have an if, there must also be an else. You can't just have an if by itself, okay? Because otherwise, your program won't even compile, okay? So with Racket, if you have an if with Racket, you must have an else, okay? You must, right? There's just no, otherwise it's not going to work. So in Python, you can have an if by itself because Python follows different rules, okay? Okay, so here we're going to do for x in x's, result append Cartesian helper x with y's, return results. Shift enter. Let's see if this is going to work. Cartesian A, B, C, and 1, 2, 3. And it looks great. So we have A1, A2, A3. We have B1, B2, B3. We have C1, C2, C3. It works great. Okay, so again, you've got, A1, A2, A3. You've got B1, B2, B3, C1, C2, C3. Okay, this reminds me of FOIL, kind of. It reminds me a little bit of FOIL. Remember that from high school algebra? You know, when you're multiplying binomials, okay? Kind of reminds me of FOIL. Okay. So these functions were great, but there's one little issue going on over here. So the issue, wait a minute, that's not what I want. So the issue is here we have three sets. We have three sets. We have A, B, and C. Ugh. You know, I hate it when I get dirt on my computer. I try to keep it really clean. Hold on a second. Wait a minute. Oh, that's just, oops, that's, oh, that's part of the web page. Oops, sorry about that. Okay, so we have three sets here. So could I do this? What if I were to do this, right? What if I were to do, here, hold on one second. What are, A is ABC. Okay, so I have A is equal to A, A, B, C. Okay. B is equal to, let's see, X and Y. B is equal to X and Y. And I think C is equal to 0 and 1. Let's see, 0, 1, yeah. Okay. Excuse me. Okay, so we have, this is set A, this is set B, this is set C. Okay. Now the problem here is Cartesian A, B, C, but this isn't going to look very pretty. What's wrong with us? Okay, that's really not quite right. I mean, that's not working, right? That's just not quite working out. So it's sort of, I mean, it does kind of work, but it's not giving me the answer in a form that's going to make sense to me. Okay? So what can I do about that? Is there a way that I can, try to work around this problem? Okay? So there is a solution. So you have to take a look at what's actually happening over here. You have to take a look at what's happening. You have these lists that are nested within lists that are nested within lists. So what would happen if you mapped the flatten function? So when you flatten something, when you flatten a list in Mathematica, right, this is what's going to happen. Chachk, it's okay. I'm talking to my dog, guys. Oops. Oh, flatten. Oh, this is not good. Okay, flatten's not defined, so we have to, okay, that's bad. Flatten is defined in Mathematica and it's defined in Racket, so we're going to have to define it for ourselves, okay? So, yeah, that's, okay. So let's define the flatten function. Define flatten. This is going to have to be recursive, I think. So define a list of lists. I'm going to call it x's, right? X is 0. Oh. That's going to be the head of the list. And the tail is going to be the rest of the list. If the type of the head is equal to list, then we're going to have flatten head plus flatten tail. Okay. Else return the head added to the flatten of the tail. Okay, so what does this do? So if I have a deeply nested list like this, deeply nested list, oh, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's kind of a problem if I'm doing something like the Cartesian product. So flatten deeply nested list, and I should just get, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in one list, right? Index error. Oh, I know what happened here. Let me go back up here. I forgot. If not bool x's, then return x's. I don't think I'm going to need an else here. Will I need an else here? Let's see. There we go. Okay. So, yeah, you have to handle the case of the empty list, which is what I forgot to do originally. You have to handle the case of the empty list, which is what I did here. So this is my, oh, wait a second. Why am I not? Okay. Deeply nested list. And then flatten deeply nested list. Oops, that's not, wait a minute. Deeply nested list. Oh, nested list. There we go. Deeply nested list. So it transforms the list of lists, the list of lists of lists. Okay, it changes it into one list. So we can use this function over here when we're solving this problem. All right. So what if I have something like this? Cartesian, AB and C, right? And that's really doesn't look right. So then I'm going to say map flatten, but it's going to return a generator, and that's not what I want. I want a list. Okay, so that's not quite. Yeah, so okay, so that's not quite, wait a minute, let me see something here. AX, AY. Yeah, but that's still not quite what I want. So what if I were to do this? What if I were to do this? So if you have Cartesian AB, wait a second. Why am I getting... Oh, I see what's happening here. You know what? With my Cartesian function, I'm getting, these are too deeply nested. Yeah, the one thing I don't like here, look at how I have a list of lists of lists. So this part here needs to be changed. Now I see, okay, now I see what's happening. So let me see, hold on one second. So hold on one second. There we go. Let me see if this is going to be a little bit better. Yeah, that's okay. Okay, now that makes more sense. Because before I was getting, yeah, I was getting like this triple nested list structure, and that's not, okay, that wasn't working. Okay, So let me, okay, so much better, much, 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 much better, much better. Okay, excellent, excellent. This is exactly what I want. Okay, so the problem was right over here. I didn't want to do an append. I wanted to do, excuse me, I wanted to do a direct list concatenation right over here, whereas before I had, results, result append, and that was not giving me what I wanted, okay? I wanted to do a direct list concatenation, which makes a lot more sense. Okay, much better. Now it's starting to shape up a little bit. Okay, so what I could do here, in order to create, let's see, Cartesian helper, Cartesian. So what I'm going to do here to define the general Cartesian product function. All right, the general Cartesian product function. And here I'm going to just have x's, and that's star. Star x's means I'm entering as many arguments as I like. I'm entering as many arguments as I like, okay? I'm entering as many arguments as I like. So here, and I believe that's returned as a tuple. Let me see something. Print x's. Oh, wait, no wonder. Define. Okay, sorry about that. So Cartesian product 1, 2, 3, 4, 5, 4, 5, 6, 7, 8, 9. Yeah, it's being returned as a tuple, but I think that's still going to be okay. I think it's not being returned as a list, it's being returned as a tuple, and I think that'll still work. If not, we can change it to a list. That's really not a big deal. So let me just erase that. Okay, reduce Cartesian x's, map, flatten, and I want the whole thing changed into a list. Okay. What just happened? I think that's okay. There we go. Okay. And let's see, Cartesian product A, B, C. It worked beautifully. So yeah, I didn't have to change this into a list. It was transformed, during this whole process. Remember, the star x's means you can supply as many arguments as you want. 2, 3, 5, a million, well, probably not a million. I don't know if your computer's memory is going to handle that. But so, yeah. And so this is what we're getting as an answer. This is what we're getting as an answer, okay? So, well, let's see here. Hold on a second. AX0, AX1, AY0, AY1, AY0, AY1, BX0, BX1, BX0, BX1, BY0, BY1, BY0, BY1, CX0, CX1, CX0, CX1, CY0, CY1. Okay, so it should be the first choice. Oh, that's going to be, wait, sorry. That's going to be number 4, that's ABC. That's number 4. That's the cross product of ABC. What about CAB? Cartesian product of CAB, because the order makes a difference. Okay, CAB, the numbers come first. So CAB, we're gonna have 0, 0, 0, 0, 0, 0, 1, 1. I believe it is going to be, that's number 1. And the CBA, because C is 0 and 1, I'm pretty sure this is going to be number 3. This should be number 3. You can tell just by looking at it because the 0s and 1s come first. So that's kind of a no-brainer. BBB is interesting. I'm pretty sure this is going to be number 2, but we can see. We can check. We can check. So that's going to be Cartesian product of B, B, and B. Okay, so XXX, XXY, XYX. This is what you're getting here. And this is, XXX, XXY, XYX, XYY. That's 1, 2, 3, 4. So this fourth one is XYY. 1, 2, 3, 4, XYY. Yeah, we're getting the same thing. So that should be correct. Check my work. Ooh. Oh, I got these flipped around. Oops, sorry about that. I should have, okay. Wait a minute. I got these flipped around. So this is number 3. This is number 2. Wait a minute. And this is number 2. Okay. I think, oh, no. This is, wait, this is number, whoops, what did I do? I think I screwed that. Okay. Wait. Yeah, there we go. Okay. So yeah, I got those two I should have just done them in Python, but yeah, I got them kind of mixed up. So anyway, that's number 30. That's number 30. So let's try the next one. Oops, I did not mean to do that. Identify the cross product of A, B, and C. Okay, so A is, okay, ABC, XY, 0, 1. I think it's the same one we've been working on, right? So oops. Hold on, guys. Okay, so I had to answer the phone, answer the door. Okay, so let's continue. So, what do we have here? A, B, C. This is the same thing as last time, right? Yeah, this is the same thing. So why are they asking this question again? How weird. Okay, so the cross product of ABC, Cartesian product ABC. Okay, so we have AX0, AX1, blah, blah, blah. Let's see. So AX0, AX1, AY0, AY1. You know what? I think it is the second one. Okay, that should be the second one. Very good. CBA. Cartesian product. CBA. So 0xa, etc., etc. Let's see, 0. Oh, wait a minute. Wait. 0xa, 0xb, 0xc. So it should be 0xa, 0xb, 0xc. Yeah, it should be this one over here. Terrific. CAB. Okay, 1 second. CAB. CAB. 0AX. Let's see. 0AX. It's going to be this one. Wonderful. Okay, so then we have BBB, the cross product of BBB. Okay. So I'm pretty sure it's going, wait a minute, wait. They're trying to trick us here. Hold on. 1, 2, 3, 4, 5. So the fifth one, yxx. 1, 2, 3, 4, 5. Yeah, they're trying to, hold on a second. Let me let me see something. Let me try to make this a little bit smaller. Okay, so we have xxx, xxy, xyx, xyy, yxx, y. Okay, this one is wrong. This one is wrong. They're trying to trick us. They're trying to trick us here. So, x, y, x, y, y, x, x, y, x, y, x, y. Yeah. So it should be the first one. Very good. Okay, so this one's a little bit different. Okay, so A is equal to the set 0, 1, 3. A is equal to the set 0, 1, 3. And identify the cross product of A with itself for the given set A. So this is going to be cross product of A with itself. Oh, sorry, not cross product, Cartesian product. I'm thinking of a different course. Cartesian product. Let's see. Or CP in print CP. Okay, so we're going to have 0, 0, 0, 1, 0, 3, 1, 0, 1, 1, 1, 3, 3, 0, 3, 1, 3, 3. Okay, that's correct. Okay, same thing as before. Actually, this one, guys, you can do this one on your own, right? I mean, this isn't that difficult. True or false? Okay, let's try it. If A is equal to the set of A, what is the Cartesian product of A? And that is true. Okay, well, we can't check our work, but it is, we can see from Python that it's definitely true. It's definitely true. Let's do this one. If A is equal to 0A, A is equal to 0A, the Cartesian product of A is let's see, 0, 0, 0, 0, 0, A, 0, A, 0. This one is wrong. 0, 0, 0, 0, 0, A, 0, A, 0, 0, 0, 0, 0, 0, A, 0, A, 0, 0, A, 0, 0, A, 0, A, 0, A. This one, the last one is correct. Okay, Josh, you'll get more treats in just a few minutes. Just talking to my dog, guys. Don't worry about it. Okay, number of elements in Cartesian product of sets. How many different elements does Cartesian product of A with B have? If A has M elements and B has N elements, that's going to be M times N. M times N. Okay, so if A contains M elements and B contains N elements, then their product, the Cartesian product, will contain M times N elements, which is logical. It's very logical. Okay, so here we get into the union of sets and stuff like that. So how long is the video? It's getting there. It's getting kind of long. So let me just go over one more thing with you guys, and that's going to be enough for today's video, okay? Okay. Not quite. Hold on 1 second. There we go. Now, the thing is, what if we have something like this? What if we have something like this? Cartesian product. Hold on one moment. Cartesian product of 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. So this is going to give us all the possible tuples, all the possible, some people call them permutations. This is going to give us all the possible permutations. I think a permutation is really a little bit different, but some people will call this permutations. Okay, the number, all the different permutations. 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 2, 1, 1, 2, 2, 1, 2, 3, et cetera, until finally you end up with 3, 3, 3. This is actually very useful. This is this is very, very useful. Is there a way we could do this? So we have to think about this, right? So let me think for a moment on how to repeat. Well, now just one moment here. I think we're going to need reduce again, because we're going to need to use reduce again. So if I have define permutations k is an integer, and then I have a set. Let's say it's a set. I'll call it a set. I shouldn't call it a set because that's a reserved word in Python. A set. I'll call it, okay, I'll just call it a set. Call it whatever you want to call it. Or you can call it ST. ST, an abbreviation of set without the E. So then we're going to say, ST for M in range K, and I'll show you what that is in a moment. Arguments, okay. So what does that do? What does that do? So let's say I have a list. Sum list is equal to 1, 2, 3. And I have sum list in range 4. Oh, no, sorry. Sum list for M in range 4. So the list 1, 2, 3 has been repeated 4 times. Chach, I'll give you treats in a moment. You have to wait. So I have some list repeated, so 4 times. We have 1, we have 2, we have 3, and we have 4. Okay? Makes perfect sense to me. Or what if we have 6? Same idea. So 1, 2. I'll give you a treat soon. I am busy right now. Sorry, guys. 3, 4, 5, 6. Okay? Makes perfect sense, right? But the problem is you cannot, excuse me, you cannot supply this entire list to the Cartesian product function because the Cartesian product function expects these sublists to be provided individually, separately as individual arguments. You can't just supply them as a single list, right? So that's the issue. So if we can use reduce to change that. We can use reduce to change that. So then we're going to have reduce Cartesian product, and then my args, and that should do the trick. So let's see. Permutations 3, 0, 1. Works perfectly. Okay, guys, I'm losing my voice here. Sorry about that. Okay. Sorry. Okay, so this works beautifully. So I have 2 elements in my set. I have 0 and 1. And I'm looking for the ways, the different permutations, with the understanding that each permutation has a length of 3. So let me say that again. Let me repeat this again so you really understand it. My set or my lists, I'm using a Python list to represent a set. And that's okay to do that. Remember, a set and a list are very similar, but they're a little bit different. So for example, this list is okay. Like this, you can jump up, it's okay. This list is okay. This is not a set. This is not a set. How come? Because the 2 is repeated. So in a set, you do not have repeated elements. In a set, you do not have repeated elements, right? Also, if we're talking about lists, you got to remember that 0, 2, okay, if we're talking about lists, 0, 2 and 2, 0 are not the same list. They are not the same list, right? And you can see that in Python. Is 0, 2 equal to 2, 0? And the answer is no, they're not. But what if I change them into sets? Is 0, 2 equal to 2, 0? And the answer is yes, because in a set, the order of the elements is irrelevant. The order does not matter. Okay, so sets and lists are similar, but they're not exactly the same. They're not exactly the same. What's interesting, though, with Cartesian products, you're really thinking of your set as a list. You're really thinking of your set as a list because obviously there is some meaning to the order when you have a Cartesian product. So that to me is kind of interesting. When you have a Cartesian product, the arrangement, the order seems to make a little bit of a difference. And yet in theory, it's not supposed to. Okay, in theory, these are not the same list, but they are considered to be the same set because in a set, the order is irrelevant, right? And also in a list, like I said, this is okay. This is okay. In a list, you can have repeated elements. In a set, this is a list, right? This is a list because in a list, it's okay to have repeated elements. But in a set, It's not okay to have repeated elements. And you can see this in Python. If I change this into a set, what do I get? I get 1, 2, right? The repeated elements have been removed, right? The repeated elements have been removed. But you can always change it back into a list if you want to. You can do list sets 1, 2, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, and that's okay. You can change it back into a list, which is kind of interesting. So here, let me make this very clear to you. I'm taking a list of 2 elements, 0 and 1, and I want to see the different ways in which these elements can be combined. I want to see all the different permutations with the restriction that each permutation has a length of 3. A length of 3. So what if I wanted to see this? Permutations 10, 0, 1. That's going to be pretty big. That's going to be, that's big, right? That's going to be pretty big. You have 0, 0, all zeros, and then mostly zeros and a 1, and right, you have all these different combinations, and it's actually going to be 1,024 combinations. And how do I know? Length permutations 10, 0, 1. This has a length of 1,024 because 0, 1, I have 2 choices to the power of 10. That's 1,024. Why is it 2? How many choices do I have? I have 1, 2. I have 2 choices. 2 choices to the power of 10, right? And that's going to give me 1,024. Okay, and in Python, that's how you do exponentiation, 2 to the power 10. Okay? All right, guys, so this is interesting stuff. You're going to need to know some of this, for later chapters. I think especially chapter 7, I believe. So in chapter 7, you're going to need to know something about permutations, maybe chapter 5, but definitely chapter 7, okay? So this is all good stuff. Everything I'm teaching you here is good stuff. And remember, can you do this in Racket? Absolutely. Can you do this in Mathematica? Absolutely. Can you do it in Python? Well, I just showed you. You can do it in Python. It's easy. All right, guys, you just have to think about it and think, you just have to kind of, think about what you're doing. So these are the functions that I used. Cartesian. Excuse me, I'm losing my voice here. Cartesian, you need to import reduce. You need to import reduce from the func_tools library. You have the Cartesian helper function, and one second, and you have the Cartesian function here. Remember, originally I made a little mistake here. I had to correct it. Okay, and then here, you have your flatten function, which we need for the most general case of the Cartesian product function. The Cartesian product function is right over here. Remember, guys, reduce is important because reduce takes a function of 2 arguments and applies it to more than 2 arguments. Okay, so for example, and you really should know what reduce does because it is really important. So let's say I have a function here, define times AB, return A times B. Okay, that's really simple. Times, 1, 2. Times, 5, 6. Okay, that obviously. But now what if I want to do this? Times 5, 6, 3. So 30 times 3 should be 90. It's not going to work. It's just not going to work. Now I could do this, right? 5, 6. And then I could do this, but what if I have a lot of numbers? I mean, that's going to start to get pretty crazy. Times, times, 5, 6, and then 3, and then 4. I mean, that's going to get kind of crazy, right? So what if I just do this? Reduce times, and I have a list 5, 6, 3, 4. Okay, so what reduce does, what reduce does, and it's the same thing as fold. In Mathematica, it's called fold. Well, it's actually capital F. And then in Racket, you have fold left and fold right, it depends on whether you want to start at the beginning of the list or the end of the list. So that's a little bit of that's a little more complicated, but it's not that complicated. So it depends on whether you're starting at the left end of the list or the right end of the list. So these are in Racket. This is Racket. Okay. Those are Racket functions, and this is Mathematica. That's, I'm just going to say Mathematica, okay? I'm not going to spell out the whole thing. That's Mathematica. So in Python, it's called reduce. So instead of doing times 1 times, oh, this is just going to get so crazy, right? Times 3 times 4. I mean, this is just nuts. I mean, it's too much, right? I mean, wait a second, how, oh, there we go. So is it, oh, for God's sakes. Oh, times, here we go, times. Okay, so it's a lot of, how do you read that? How do you type it? It's so crazy. So instead, why don't we just do this? Reduce times 1, 2, 3, 4, 5. Really simple. So the whole point of reduce or fold is you have a function of 2 variables, but you're applying it to more than 2 arguments. Simple idea, a very powerful idea, because that way you can avoid this, this is a giant mess. This is a mess right over here. That's a mess. So we're trying to avoid, all of those nested function calls and a million parentheses, right? Makes perfect sense to me. And if you use it correctly, you can end up with some really powerful functionality. Okay? All right, guys, I think that's plenty for today. I think we did enough, and it's time for dinner, right? It's time for dinner and a nice movie. So I will communicate with you soon, and I hope these videos are helpful. And that's about it, okay? So we will communicate at some point soon. Have a great weekend, have a great week, and I'll talk to you later. Bye-bye.